Hello and welcome to today's webinar on GPSX version 6.1. My name is Spencer Snowling and I've been part of the development team here at Hydromantis for the past 12 years or so. And today's webinar is going to be introducing the new features and new models that are part of GPSX version 6.1. So GPSX was released, 6.1 was released last year at the WEFTEC conference in Los Angeles. Those of you who are regular subscribers to our maintenance program will have received your new versions. If you haven't, let us know. And so today's webinar is going to describe new features from the interface side, our Monte Carlo Analysis tool and our automatic layout history tool, as well as two of our newest models, our UASB model and our sludge disintegration model as well. So our Monte Carlo Analysis tool is a part of the Analyzer feature in GPSX. And Monte Carlo Analysis allows you to run a large number of simulations while using a range of inputs specified by a distribution, and then observe a large number of outputs also specified as a distribution. So you can look at the probability of something happening by picking a number of parameters and specifying their internal distribution.
Input distributions for the input parameters that are part of your model. So you select a number of parameters for which you would like to do your analysis, and you specify a distribution and a range of values for each of those parameters. So you can do as many parameters as you like, and for each of those you have to specify that you are going to show a normal distribution or a uniform distribution and so on. So we have three types of inputs that are available in GPSX. So a uniform distribution, basically showing you're likely to get an equal probability of getting any value within that range that you've specified, a normal distribution or a log normal distribution. And so we have seen some evidence in the literature that many parameters that are a part of the ASM suite of wastewater models do observe a normal and or a log normal distribution within the behavior that you see in normal wastewater treatment plants. So these are the ones that are available to use. You may want to choose one or another based on evidence that you have at your plant. If you are looking at influent flow, for example, you may have enough data to determine what that distribution should look like exactly. Okay, so what I'm going to do is I'm going to show you a layout here, which is part of actually tutorial 11 in GPSX. So we have a very simple wastewater treatment plant in this particular case, and I'm going to show you the input distributions that we selected. So now I've already run the simulations in this particular case, but so you can come here, select that I want to do a Monte Carlo analysis, and I have selected that for this particular value, the alpha associated with the aeration oxygen mass transfer, I want to have a range where I'm going to select values that are between 0.4 and 0.7, and I'm going to use a normal distribution in this case, pardon me, a uniform distribution in this case. So what's going to happen is when I run these simulations, and we're going to run 1,000 simulations, GPSX is going to select a new value for alpha each time, and it's going to do it in a manner that will give it a uniform distribution of those 1,000 values that are going to happen during those 1,000 runs. So I'm also going to, at the same time, take the maximum autotrophic specific growth rate and use a normal distribution in this case. So in addition to specifying the range here, I'm saying I'm going to allow it to go between 0.5 and 1.2 1 over day. I also want that to have a mean and a standard deviation as specified in that menu. So I want to have a mean of 0.75 and a standard deviation of 0.1. So that means that when GPSX has generated 1,000 values of this particular component, if you plot them, then you'll get a normal distribution. So I've already run this. This takes about a minute to run, or a couple of minutes. So I already ran that ahead of time. And what you'll see here is that this is a distribution of the values that GPSX selected for our maximum autotrophic specific growth rate. So here it is. There's the mean that I specified at 0.75. It's within the values that I had, and certainly that looks like a roughly normal distribution. If I had run possibly 10,000 simulations, it would look even smoother. So here's my uniform distribution. You know, pretty good, not too bad. This is a little lower than normal, but this is showing you that we are randomly generating the numbers every time. Okay, so now what we're doing is we are then solving the model for steady state at every one of those steps. And you can plot any number of graphs like you would normally in GPSX and be able to get a probability distribution. So now this plant is being loaded with approximately 25 milligrams per liter of ammonia, and it's nitrifying most of the time. So what I did was I fixed everything else in this particular model, such as the airflow rate and the SRT and so on. And I allowed the amount of alpha to change, so therefore you're getting slightly better oxygen transfer in some simulations than others. And actually you're getting a little better growth rate in some of the nitrifier growth rate in some simulations than others. So when I run that and I look at a distribution of the ammonia in the effluent, which is what this graph is in green, we can see here that in many cases, and a majority of them down here at this level, we're getting you know, 2, 3, 4, 5, 6, 7 milligrams per liter of ammonia. So it's mostly fully nitrifying most of the time. And there are another sort of range over here where we're getting partial nitrification. And then this big bar at the end, of course, is the ones that don't nitrify at all. So the nice part is you can look at this distribution and you can see that, well, for the size of this particular plant, I know that I'm going to get, you can plot this line directly on the graph that says my effluent ammonia will be less than 10 milligrams per liter 46 or 47% of the time. So I could go back, make my plant a little bigger, and see how much of that distribution that I can push down this way and see approximately what I need to do in order to make the probability of coming in above the effluent limit as small as possible. So this is a way of sort of looking at what's the probability that I'm going to exceed my limit, and I can run a simulation. I can go back, edit, or make changes to the design, run that distribution again, and see whether I get a better performance based on probabilities. And you could even say that I know some parameters better than others, and it allows you to do a fairly sophisticated type of uncertainty analysis with your mathematical model. So I like using Monte Carlo types of analysis quite a bit, and if you have any questions about it, feel free to give me an email at any time. Okay, let's go back to the slides. So one of the limitations that we have at the moment is that currently the way that we've implemented this Monte Carlo analysis, it assumes that all of those inputs, like the two that I was showing there, the growth rate and the alpha, are uncorrelated. So that means that one number is sampled independently of the other number. There are indications that certainly there are parameters in the models that we use in our industry here where things are correlated together. And certainly if you were to put up some influent concentrations, for example, those things would be correlated. When you have high TSS, you're more likely to have high BOD. So those methods require a way to sort of correlate those parameters together. And that's what we're working on. So right now we're assuming uncorrelated, and then we're going to have a way to correlate those numbers together in the future. We're also looking at ways to implement Latin hypercube sampling. So what that will do is provide us a way to get a really good evaluation of what the distribution of outputs looks like without having to run tens of thousands of runs. You can basically get the same results of running fewer simulations. And as I was saying, the one that I showed you now only took a couple of minutes to run, so it's not too bad at all. But if you really wanted to get more detail, you can do that. So those are coming in the future. Okay. I notice I see a few of us people have questions. I think what I'll do is I'll come back to the questions at the end of the presentation. Okay, so the second software feature that is available in the new version of GPSX is a layout history database. So the new version of GPSX now has database functionality in it, and it automatically makes a backup of your layouts as you use them and as you save new versions as you go along. So this is for a couple of purposes. One, it's a little safer just to make sure you always have a backup of what you're working on, but it also is a bit like version control. You can also make notes about the changes that you've made as you've gone along, and you can always go back and retrieve a previous version of your layout at any time. So this is going to happen sort of in the background of your model, pardon me, of your layout anytime that you're using it. So now you have to first turn that on if you want to take advantage of that. We need to go to the Options Preferences menu, turn this value on, and then the history feature will become available in this menu. So now once it's turned on, it'll automatically start working. It'll automatically start making those backups for you. You'll be able to come here to the history menu, and then you'll notice what an entry in this database for every layout that you've loaded and made use of while you're using GPSX on a regular basis. So for any one of those, you can then select that. You can then open up the history of that particular database, and you can see the versions that have been used. So as you're using the model and making changes to it and hitting save, it will save a new version, but it'll keep the old versions that you've been using before as well. So you can always slide back. You can use the notes field here to add notes as you were going along, and you'll always have a version of the older ones that came along. So it's a way to protect your work, keep an automatic backup. You can it's a way of kind of undoing changes if you decide you've progressed down a route and I would like to go back to a previous version, and it's a good way to sort of manage your information. There are some limitations at the moment. It only backs up the layout files themselves. It doesn't back up the data that goes with it if you have a lot of data that's being read in. It's obviously that's a database, so it's going to grow in size as you use it more. It's actually a fairly efficient database, so it doesn't take up a lot of space, but it can do so if you make a large number of saves over time. And right now, multiple versions of GPSX that are being used at the same time on the same computer can't access the database together at the same time. So, but in general, it's a useful feature, and I've been using it since version 6.1 came out last year. Okay, so that's the new software features that we've added to GPSX. And so now I'm going to cover the two new models that we've added, and the first one being an upflow anaerobic sludge blanket model. So we've had requests for the UASB model for quite a few years. There is ways that you could have done that before, which I'll talk about here in a moment. But we actually developed up as part of a project that we were working on a really rigorous, nice, very robust UASB model that's easy to use, and we liked it quite a bit, and we put it into GPSX, and it is now available. So when you're modeling a UASB reactor, it's a fairly complicated system. Actually, there's a lot going on there compared to just modeling a conventional activated sludge completely mixed tank. You've got the granules that are growing, you have some mixing happening, you have some gas release, you have some solid separation, and everything kind of going on together there at the same time. So if we were going to put one together, we felt that we needed to have a reaction model, obviously, to do the anaerobic treatment. We needed to have a hydraulic model to indicate how things are going to change if you increase the loading and the way that granule bed is going to increase. We needed a solid liquid separation model, obviously, to be able to keep the granules in there. We have to get the gas out through a separation model for the gas. And we need a fluidized bed model and some sort of substrate transport and utilization model. So there's a lot going on there all together at the same time. There was the possibility to go down the route of the one-dimensional diffusion models like our biofilm models. There was a lot of complications with that because the granules themselves kind of grow and change, and the surface area on them changes as well. So what we decided to do was to create a model that allows us to do the biological treatment part in the way that we would do normal anaerobic digestion in a completely mixed manner, but then we also impose a granule bed on it as well. So we can do the solid separation in a way that is relevant for the growth and settling and packing of a granular bed, but we still get all of those nice anaerobic treatment reactions in there as well. And we get that sort of mechanistic approach that everybody likes. That is the big value of having GPSX, but we still haven't. But we still allow sort of relative ease of use of the model in terms of its calibration to do the solid separation part. So we, in the past, and I know some people have already been using this for some time, you could always sort of stick down an anaerobic digestion unit and follow that up with a solid separation unit and a recycle in order to be able to do that reaction, and then you sort of kept all your solids together there. But what we've done now is we've sort of incorporated those two things together. So we have a built-in solid separator unit that's based on the granular sludge bed model, built right into the reactor, along with that gas transfer, pardon me, the gas liquid separation model going on as well, and it's all together in one particular unit. So you will find that unit only for the new Mantis 2 model. So you have to go to the top of GPSX, do the pull-down menu, go to the comprehensive library, the one that models carbon, nitrogen, phosphorus, and pH, and all the inorganic precipitation and so on. That's our Mantis 2 lib library. And once you have pulled down and selected that model, you'll notice that the objects available to you in our process table are changed, and there's a new one added there, the upflow anaerobic sludge blanket. So that way you have the new object, but it's available to you only in the Mantis 2 library. So that's what it looks like, this new object. See here in that solids, pardon me, the attached growth processes table. It's the bottom one there. And in addition to entering in, obviously the usual thing is reactor size and operation, you're going to be asked to provide some of these bed fluidization parameters. These are going to be the ones that we're going to use to predict how high that granule bed has grown, what that mass of granules is in there, and then how that's going to lead to the solid separation. From that, you can then, of course, predict a number of interesting things, such as the granule density, the volume of the sludge bed, and the sludge blanket height. So those sorts of things are now available to be plotted along with all of those effluent quality parameters that you would normally be looking for. So I'm going to run a short demonstration of that here. So let me get the Monte Carlo thing out of the way and hop over to my UASB layout. So in this case here, I'll just show you briefly, we have an influent coming in that's bringing in some sort of wastewater stream. We have a dosage of alkali to control the pH, so that's going to be controlling the pH that's going on in here. And then we have our granular sludge bed reactor. So this is a very short simulation where we are going to demonstrate what's going to happen while the influent flow is increased for a period of time and then drop down back to the original level. So just going to run that simulation here. You can see this is showing the solids mass and the sludge blanket height in this particular reactor. So we just stepped up the flow here just to give it a little step flow, just to give it a little stress testing. And you can see here that the solids mass remained the same, but the sludge blanket got fluffed up a little bit. We can see here that there was some change in the actual performance because we were overloading briefly here. Our gas flow went down. The gas flow went up, but of course the CH, the methane fraction, went down briefly. Our effluent quality was being challenged a little bit while that was going on. But you can see here that you can get the usual sorts of information out of that model in terms of the prediction of its effluent quality, and then we have all of the gas production and conversion rates and all of that stuff is available as you would normally expect to find in our quick table in GPSX. Okay, so I will just pop back to the slides here and wind up the session today by finally talking here at the end about our sludge pretreatment model. So this is also a new object in GPSX, and this is for places where you have sludge treatment and you want to be able to do some sort of either thermomechanical or chemical breaking down of those solids and trying to get inert and other particulates broken down into something that's a bit more biodegradable. So again, this is a unit process that we've had requests for over a number of years. We've done a number of different things, and what we've done here is tried to make a bit of a generic model that can do many different things and can simulate these number of different types of processes. So this can include sludge heating, microwave, treatment through sonic methods such as the open cell process, or through chemical processes, ozonation, for example, like the BioLeader process. Those are all kind of treated differently. You use different inputs, whether it's the mechanical process or whether it's the chemical process, but ultimately it's going to take us down the same pathway to, convert the particulate and some of the inert state variables and move those over to being more biodegradable, more readily biodegradable state variables, and then do all the mass balances on the nitrogen and phosphorus and other things that go with that. So essentially, we're converting particulate organics into soluble, and we're also converting inert inorganics into biological substrate, biodegradable substrate. So we have some default values set up here. We have also implemented an efficiency into the model that you can calibrate. So the relationship between the amount of conversion that you get and the amount of input that you're providing, whether that be energy or chemical, we have a half saturation coefficient applied so that you can calibrate the model, so that you can see that there is a drop off in efficiency as you try to go to higher and higher levels. So I'm not going to dwell on these mass balance tables here, but just to say that this is the kind of information that is available in our technical reference to describe what is actually going on in that model. So where we take the organic biomass and we move it over to particulate substrate and soluble substrate. We also move some of the inert inorganics around. Some of it goes to SS, some of it goes to soluble inert, some of it goes to XS. And we also do directly from XS to SS as well. So these are all sort of going on simultaneously. The rate and the amount of COD that's moved from one state variable to another will be a function of the efficiency table that you're using, that half saturation curve, and also the loading and other things that are happening there. So what the two main things that we've been seeing this used for, one is treatment of your WAS before you bring it back to your bioreactor to improve denitrification, give yourself a bit of a carbon source to work with there, or a pre-treatment of your wasted sludge to improve digester performance, hopefully get a bit more gas production and recover some of that energy. So we've used this. We just finished up a very large project where it was one of the key components, and we had a good chance to test this model and develop it, and that's the part of the driving force that was allowed us to develop a good model and put it into GPSX and make it available for all of our users. So I'll just briefly show what that looks like. Again, this is something that's only available in the Mantis 2 library. So just to show you what the new object looks like, it's this one here. We can sort of see, because we were describing many different types of processes, we made a generic object that kind of showed large particles being broken down into small particles. But the idea is that you have some sort of COD coming in one form, and then we break that down. You can notice here that we're having a decrease in the VSS as it goes across there. We're breaking down some of those solids, and the readily biodegradable soluble BOD is going up. So it all mass balances nicely, and it is a relatively efficient model. It's a bit of an empirical thing, but we've had some pretty good success with it. Okay, so I think I'll wind up the webinar here. Just by having a few mentions of things that we've got going on right now at Hydromantis. First of all, I'll mention that we also released our first phone app this past fall. So we have the tool called Water Units, which is available, first of all, for Android. It's only available for Android at the moment. We actually are working on the BlackBerry version right now. This is a tool. It's essentially the units conversion functionality from GPSX, but put into a phone app. So if you're ever working just manually on calculations, and I would like a nice way to calculate, move things between MGD and meters cubed per day, then you can do all those unit conversions back and forth. And we've made it focused mostly for the wastewater industry. I also mentioned that we've added some more new videos to our library. So for some of our other projects, such as TalkChem and CapTetWorks, we now have a complete full suite of all of our tutorials and instructional videos are now available. And you can access those by selecting the Videos tab at our website. We have been enjoying actually quite a good increase in the amount of training that we've been doing remotely by webinar recently. So I'll just mention that you can get training for GPSX. You can get a nice refresher course, which includes discussions of all of these new models. We still offer the flying out to see you at your office services, but we also offer a complete GPSX training package that's delivered via the GoToWebinar service like we're using today. And you will be receiving actually an email and an offer about that in the next week or so keep your eye out for that. We also offer this for other packages for TalkChem and CapTetWorks as well. So, and as always, we are always available to help you out with your consulting jobs, to help build models and calibrate them for you. We also offer services whereby we can customize our models for you, either both the model content itself or customize some interfaces to put on the front end. And I'd like to invite everybody to our next educational webinar, which is going to be talking about TalkChem version 4.0. It's 2 weeks from today at the same time, and you can register for that at our website by clicking on the webinars tab. So lastly, I'd like to thank everybody for coming. I'm going to stay online here for a little bit and answer some of the questions that I see have been typed into the questions window here.